I have the great pleasure of introducing our speaker today, Professor Denise Mauzerall from Princeton University, a joint appointment in C-PREE, SPIA, and in the Department of Civil and Environmental Engineering. Now, when I arrived here about 22 years ago, C-PREE was a much smaller faculty, and there was this one young assistant professor surrounded by the usual constellation of silverbacks and such, and that was Denise. And from the start, I was astounded by the work that she was doing, which focused a great deal on issues of air pollution. And in particular, she was always looking for ways to address air pollution issues that affected human health that simultaneously carried other benefits with them. And over the years, as she has gone from that assistant professor to now a shared full professor here, she has increasingly turned her attention to the issue of climate change, but never losing sight of problems that air pollution poses for human health, independent of climate change, and not stopping in her quest to find ways to, and this is a very painful analogy for me to make, ways to kill two birds with one stone. And it's really an exciting body of research. She has also increasingly focused her attention on these issues in key nations such as China and India, and in the process of doing that has built a lab that has an awful lot of people from China and India who have subsequently gone on to be really important researchers around the world, as well as back in their home countries, following in her footsteps. So it's a real pleasure to have Denise as a colleague, and it's an even greater pleasure to welcome her here so that you get a chance to hear about her research on these issues. Denise Mauzerall.
Thank you, Professor Wilkov. It's great to be here. Thank you all for coming. It's a pleasure to have an opportunity to share with you some of the work that my group has done focused on China. I gave a version of this talk repeated times actually this spring in China at nature conferences at Tsinghua, at Peking University, and it really highlights the work, some of the best work I think that my group has done in the last 5 or 7 years or so at Princeton with a focus on China. As David mentioned, the group's work is now also beginning to look more and more at India, and we're doing some work also on the US, with an eye always to looking for opportunities to capitalize on co-benefits and synergies for reducing air pollution emissions and greenhouse gases simultaneously. So why China? Why did I start looking at China? I came to Princeton 25 years ago now, and I felt as China went, thus would go the world. China's economy was booming. Its emissions of air pollutants were increasing. It was soon to have the worst air pollution problems in the world. I was trained as an atmospheric chemist. I'd spent 4 years in Washington, D.C., both working for an environmental consulting firm and for EPA. And I just thought, I really want to be in a place where I can do work that really makes a difference. And if we can understand and facilitate a transition in China, that would be highly valuable. So China is by far the world's largest emitter of CO2. It's made a commitment to peak carbon emissions by 2030 or sooner, and to be carbon neutral by 2060. So it's simultaneously continuing to build coal-fired power plants and also deploying more renewable energy than any other country in the world. It's historically had terrible air pollution problems, the worst in the world, now more recently increasingly displaced by India. China has been very successful at decreasing its air pollution emissions. I'll talk a little bit about how. And India is now really struggling with some of the worst air pollution in the world. In China, the central government is supporting major efforts across the economy to reduce dependence on coal in particular, but fossil fuels more broadly. And as I mentioned, it's deployed more renewable energy than any other country in the world. So here, if you look at annual national CO2 emissions from 1960 to 2023, you can see something really striking. In orange, here's China. In 1960, compared to other major emitters, it was tiny. But around 2000, its emissions started to skyrocket. And around 2000, it passed the European Union in terms of CO2 emissions. In 2006, it passed the US. And now it's more than double the emissions of the United States, CO2 emissions. It's actually not that far below all the other nations of the world combined outside of the US, India, the European Union, and bunkers, which are international emissions from aircraft and shipping. Its annual per capita CO2 emissions have also skyrocketed as its economy has developed and boomed, and the living standards in China have improved. You can see that it passed the world average in the mid-2000s. It surpassed the European Union about 2012, and now it's comparable to the emissions of Japan at a per capita basis. The US, in contrast, used to be the highest and still remains the highest CO2 emitter per capita in the world, but our per capita emissions have been decreasing steadily since about the turn of the century. If you look here at premature mortality due to air pollution, this is in the year 2000, and at that time, China and India both had the highest rates of premature mortality due to air pollution of any region in the world. Things have changed since then. I don't have a more up-to-date figure. China's air quality has improved a lot, India's has not, and actually the European Union has also improved quite significantly. In terms of renewable energy, as I mentioned, China has the most solar production in the world. You can see it dwarfs by more than doubling what's produced in the US, and then India, Japan, Germany, Brazil are also listed, but still much smaller. It's also has more installed wind capacity by far than any other country in the world, though its watts per capita is lower than Germany, which in total, because it's obviously a much smaller country, has far less in total. The US here is second. And an interesting question is, how much does solar and wind power together contribute to the total electricity generated by each country? And here you can see China, Here you can see China with about 11% in 2021. And in the last 3 years, deployment has increased dramatically. And so coal power plants have also been deployed increasingly over that time. So I'm not quite sure how that ratio has changed. I don't have more up-to-date information. But I think it's at least as high and likely higher than listed here. And you can see here the US is about 13%. And you can see Germany is one of the leaders at almost 30%. So China has this commitment to reduce its emissions, peak by 2030, and then come down to be carbon neutral by 2060. The question, of course, is what happens between 2030 and 2060? First, how high is the peak? And then how quickly does it come down? Does it come down quickly and then have a long tail? Does it stay really high for a long time and then come down slowly? That'll make a big difference in the total emissions that are attributable to China. But let's take a look at ways that they can decarbonize the economy, or how any country sort of schematically can think about decarbonizing its economy. What you see here is a schematic of total energy demand on the y-axis. That's how much total energy is needed to achieve an activity, a desirable activity, or how much total energy is needed to run the economy. And then on the x-axis, the carbon intensity per unit energy. That shows increasing carbon intensity of coal is greater than it is for gas. Gas is greater than it would be, of course, for renewables. And so you think about carbon intensity as how much CO2 gets emitted or how much carbon gets emitted to the atmosphere per unit energy obtained. So there's a demand-side approach to decarbonizing the economy, which is really important, and I think often overlooked, which is to improve the energy efficiency to reduce the total energy demand. That's super important. There's huge co-benefits of that. If you reduce your energy use, you reduce your greenhouse gas emissions, you reduce your air pollutant emissions, you need to extract less fuel from the ground so you don't disrupt land processes, you don't have coal mine tailings and water pollution that results. So extremely valuable to improve energy efficiency. It gets less attention than the other way to do this, which is the supply side approach. And here I would say that's to decarbonize the remaining energy required for the process or for the economy. And there you look at substituting renewable energy for coal or for gas, or potentially hydrogen from renewable energy, or electricity, et cetera. So there still remains these hard-to-abate applications, though, these hard-to-abate processes, which are typically industry processes like making steel or ammonia, where you can't easily decarbonize the remaining energy by using renewably generated electricity. You still need really high temperature heat to run some of these processes, and that's where things like green hydrogen come in. And we'll talk a bit about that later. So the goals of my group have been really to identify opportunities to reduce energy demand on the energy efficiency side, identify opportunities to decarbonize the energy supply, examine process synergies to decarbonize the remaining hard-to-abate sectors, and then to quantify the co-benefits for air quality and public health. So I'll walk you through some examples of these. So objectives: evaluate the opportunities, synergies, and co-benefits of decarbonization in the residential, the power, the transport, the industry, and the agricultural sectors. And I'm putting aside the agricultural sector for this talk because it just takes us too far afield. But before I just entirely set it aside, I'd like to emphasize that agriculture is a big source of greenhouse gas emissions. You find agriculture emitting carbon through tilling of soils. You find it emitting nitrous oxide through the use of fertilizers. Nitrous oxide is a long-lived greenhouse gas with a high radiative forcing. You find it emitting methane through anaerobic processes, both in rice paddies and in cows and other ruminants. So I'm setting it aside now just because, in the interest of time, but we have looked at opportunities to shift agriculture to become more efficient in its use of fertilizer, to reduce emissions in that fashion, and to shift diets away from meat and to more sustainable sources of protein like soybeans, and how that would also be beneficial to climate and to air quality, because when you put these fertilizers on soils, they also contribute to air pollution emissions. But the overall goal is to look at greenhouse gas emissions, air pollutant emissions and resulting concentrations, premature mortalities due to air pollution, and the costs of mitigation of interventions in these various sectors. So here's a figure I've used in the past. This is showing synergies and trade-offs between reducing air pollutants and greenhouse gas emissions. So here you see on the x-axis the change in national total CO2 emissions, and on the y-axis, sort of negative, percent change in premature deaths resulting from a reduction in air pollution. And you can have cases where you have synergies, where you get a reduction in both. And you can have trade-offs in cases where you do something that will reduce your air pollution emissions, but actually can increase your CO2 emissions. And examples like that is something that China has explored. We did earlier work on this, looking at coal gasification to make synthetic natural gas. You gasify coal, and you then have gas that doesn't have the air pollutants associated with coal. But making that energy transition costs carbon, costs energy. And so you get this gas, which you can burn cleanly and reduce your local air pollution, but you have expended additional energy. And from a climate perspective, that would be a strong disbenefit, a trade-off to be avoided. So one thing that we looked at a few years ago, this work was led by Mi Zhou, who's now a postdoc in my group sitting right over there, were synergies and trade-offs in rural clean heating options. This is a supply-side intervention. The Chinese government had a major effort, the clean heating program, to remove these small coal stoves, which use either raw coal, lump coal, or coal briquettes to provide heating and cooking in rural households. They emit a huge amount of fine particles, and it was well recognized for a long time that that contributes to very elevated fine particle concentrations indoors and contributed a lot to public health issues for the poor indoors. Earlier work that we did that I won't talk about in detail showed very clearly that those small coal stoves in the Beijing-Hebei Tianjin region surrounding the capital city of Beijing contributed about 40% of the fine particles in winter when these stoves were used heavily for heating. And so clearly then these small stoves had big problems for ambient air pollution and affected everybody, not just the poor in these households. And so we showed that that was the case. The Chinese government then started removing these stoves from people's homes and businesses. And our next question was, what should they be putting in instead? Because they need to heat in the winter. It's very cold in northern China. And so we looked at a variety of alternatives that ranged from clean coal with using improved stoves, either with coal briquettes that had low emissions or raw coal that had high emissions as possible alternatives. And then this is electricity using resistance heaters using the 2015 grid. And then you can see here air source heat pumps with the 2015 grid, natural gas heaters, air source heat pumps with the 2030 grid, and no fossil energy but with heat pumps. So what you see here is that there's disbenefits, there's trade-offs. You improve your air quality and you reduce your premature mortalities with any of these interventions. But in the case of using coal with high emission factors or resistance heaters from a coal-intensive grid, they would increase the CO2 emissions. And so this is a clear trade-off and not a desirable option, though it has been a fairly widely used option in China because all homes have electricity and resistance heaters can just be plugged in. As an alternative, air source heat pumps are a far better choice because they reduce your emissions of air pollutants. You plug them in, so you're using the electricity as the grid decarbonizes, you then decarbonize your heating, and that has big advantages. You can see here from 2015 grid, which is very carbon intense, to a 2030 grid where we expect it to be much less carbon intense, there's a big reduction in CO2 emissions. And then eventually when the grid is fully decarbonized, you get the largest benefits for air quality, health, and the largest reductions in CO2. So this is the same figure as you just saw, but now the next question is, how much does this cost? How can you actually afford this in these poor provinces? And so what you see here are the different types of interventions and the annualized cost, which is the capital cost plus the operating costs. You can see rural households in dashed lines, urban households in solid lines, and these resistance heaters turn out to be the most expensive option because they're very inefficient and they require a lot of electricity to operate. Heat pumps here's gas heaters. Gas heaters are a bit cheaper. Heat pumps turn out to be the cheapest option in annualized costs, but they have very high upfront costs. So that means you either need subsidies to cover the upfront costs, or you need some kind of loan system by which people can buy them and then spread the costs out over time. And then you can see that clean coal and dispersed coal is actually more expensive because it is relatively inefficient, but these clean coal options with improved stoves are cheaper. And so in making this move to an improved, cleaner fuel and heating mechanism, there are some additional costs that need to be addressed. Okay, well now there's also the demand side, and there's benefits to improving building energy efficiency before you install these heat pumps. So heat pumps are like air conditioners that can work in reverse. They're now used at Princeton. There's a ground source heat pump system at Princeton. They're used in our house. We installed heat pumps. They work really well, but it's really helpful to have your building well insulated before you install them because otherwise it leaks and you use more electricity to operate them. And so what we did was here look at how improving building envelope efficiency in rural areas lowers costs and emissions. And this work was led by Shangwei Liu, who is a PhD student in my group, who's now a postdoc at Harvard Kennedy School, and Hongshun Liu, who's a visiting energy economic professor from China. So here, what you can see is if the rural residential buildings move to natural gas heaters and there's no efficiency improvement, these are the associated greenhouse gas emissions, annualized costs, and upfront costs. So this is a tempting way to go because the upfront costs are low. If you go to heat pumps without efficiency improvements, you get lower greenhouse gas emissions, lower household annualized costs, but higher upfront costs. If you modestly improve the energy efficiency of your building, you can further reduce your greenhouse gas emissions. Your annualized costs are about the same, and your upfront costs are not very different. And then with substantial energy efficiency improvements, your costs go up a lot. And these rural buildings in China are really inefficient, so modest improvements clearly pay back really quickly. But the more substantial efficiency improvements are probably something to set aside and only do when you start actually rebuilding some of these old buildings that probably won't be occupied for decades into the future. So because of these building energy efficiencies and the relatively decreased household costs, it can help reduce backsliding to coal. And one thing we felt was really important was that replacing current fuel subsidies with building envelope subsidies would be a really desirable thing to do. Because if you have fuel subsidies, that encourages people to use more fuel, more electricity. But if you have building envelope subsidies, then they just use less energy, and they ultimately save both energy and money. Okay, so that's the rural area. Now let's look at the supply side on the urban scale. So one thing that's done for heating in China in urban areas is to use district heating. District heating is something that we're not that familiar with in the US, but we actually have it at Princeton. It's the idea that you have a central facility that produces heat, and then you pipe that hot water to your buildings and around, and then it comes back at a lower temperature and it gets reheated. And here you can see that in the schematic, the district heating can be provided by fossil fuels, by biomass, by geothermal heat, by solar heat, by nuclear power. At Princeton, we're using geothermal heat pumps, ground source heat pumps, that take heat out of the ground. They're basically a heat exchanger that uses the ground as a reservoir, and they then are able to transport that heat around campus. Super clean, driven by electricity. As long as the electricity is decarbonized, it's a very energy efficient, low carbon way to heat a facility. In China, they're using coal. They're not using geothermal right now. They're using coal. And if you go here, you can see the system that they're using. This is a schematic from the US EPA, but the idea is basically that they're running coal-fired power plants as combined heat and power systems. And so they burn coal, and they generate electricity. That electricity goes to the building. The heat goes to a heat recovery unit, and then it also goes to a heater, can be used to cool the building. So what's the problem with that? That was touted for decades as like the best, most efficient thing to do. What's the problem with that approach? If you want to decarbonize your energy system, you have to shut down your coal-fired power plants. But if your coal-fired power plants are heating your cities, you can't shut them down because you need the heat. So that means you have a risk of what we call carbon lock-in, that the carbon from those power plants has to continue to be released because those power plants are needed to provide heat. And so we looked at how can heat sources in China's urban district heating systems be diversified to reduce the risk of this carbon lock-in. And so we set up 4 scenarios, basically a base case, and then a high coal, a mid coal, and a low coal scenario, where we basically reduce the amount of new combined heat and power plants that are going to be used for heat and electricity in the future, from a high coal situation to a lower coal to a low coal, where The mid-coal uses industrial waste heat from steel and nuclear power plants. The low-coal uses industrial waste heat and air and ground source heat pumps, like we're doing here, to reduce the emissions. And there's no new coal combined heat and power plants in the low-coal scenario. And so we've proposed a city-level strategy to implement the actual existing government policy proposals to electrify district heating and deploy low-carbon heating technologies. And I won't go through the details of this figure except to point out that, so we were looking at the generation by different sources for each of these 4 scenarios, the CO2 emissions associated with each district heating source, and the total cost by source. And so you can see that when you look at the district heating generation by source, they're heavily reliant right now on coal boilers, small coal, CHP plants, and then some large ones, and then some natural gas boilers. And going forward, if China continues to do that, the CO2 emissions will increase. And if they're able to displace some of that, the CO2 emissions will go down. And what they can displace it with includes things like wastewater source heat pumps, air source heat pumps, ground source heat pumps. So the district heating systems won't go away quickly, but it's important that they not remain entirely reliant on these coal-fired power plants so that they can close down the coal-fired power plants going forward in order to meet their target to be carbon neutral by 2060. So what we did was we looked at a city-level strategy to decarbonize China's district heating. And we looked at each of these cities and looked at the type of alternatives they had available. And whether they could install absorption heat pumps or construct new heat transport pipelines between power plants and cities, whether they could use industrial waste heat, whether they really didn't have very much, and so then they really have to deploy heat pumps, ground source heat pumps. And then here we accepted that Beijing could use natural gas. And so you can see this diversity of options for all of these cities around China. And in this figure, I'm showing again what I showed before, but I wanted to emphasize how important this really is. Because for China to meet its target, you can see here, peak by 2030 and phase out by 2060. This is the terawatt hours of electricity generated from unabated coal. This is what's possible if they were going to meet their 2-degree target. This is what's possible if they're going to meet the 1.5-degree target. And this is what these coal-fired combined heat and power plants would emit in the high coal, the mid coal, and the low coal scenario. It's really only in the low coal scenario where they're switching heavily away from these coal-fired combined heat and power plants that there's any chance of really meeting the 1.5 or 2-degree target. It's super important that they make that move. You can see here that by 2050, these power plants alone would be emitting more than what would be allowed to meet the 2-degree target. So this is a big source of emissions to think about mitigating. Okay, so then there's also the transport sector. The transport sector also intersects with the power sector. And I'm not going to go through the details of this as much. This work was led by Li Chunpeng, who was a PhD student in my group. She's now a postdoc at Lawrence Berkeley National Lab. And then a variety of other members in our group and someone at Tsinghua as well. So when thinking about the transport sector, there's wide agreement that electrifying vehicles is a very efficient, pragmatic way to decarbonize the vehicle sector, the transport sector. But the question then becomes, where does that power come from? If the power comes heavily from coal, you don't actually reduce your emissions. If the power comes heavily from renewables or nuclear, you greatly reduce your emissions. And so what we did was we looked very carefully in China at the supply side, at the vehicle and power sectors combined. And we looked at how rapid deployment of alternative energy vehicles using the current high coal power grid will actually increase pollutants and CO2 equivalent emissions. This work came out in 2021, and our base year was 2015. The power grid is somewhat decarbonizing, and the coal power plants now have very good pollution controls on their smokestacks. And as a result, the air pollution emissions from coal have been decreased. That costs a bit of energy to do. And it also, when you get rid of the air pollutants, people are healthier. Everyone appreciates that. It's very valuable. But the unintended consequences of that is that those reflective aerosols in the atmosphere disappear. Those sulfur and nitrogen oxide, sulfate nitrate particles that are formed from the emissions disappear. And that means that the reflection of the radiation back to space decreases, which means your warming increases. I was just in India for a few weeks, and it was really noticeable there when you had haze in the sky. It felt cooler than when it was a really clear day. The aerosols really are, it's like having a white parasol that reflects the incoming radiation back to space, and it cools the atmosphere. And so reducing the emissions of the air pollutants without reducing the CO2 emissions will accelerate warming. And so it's especially important as the demands on electricity increase that we move away from coal and other fossil fuels towards renewables or potentially nuclear. So rapid decarbonization of the grid is critical to benefit from increased penetration of alternative energy vehicles. And AEV deployment will result in reduction in all air pollutants and carbon dioxide emissions when the penetration of renewable power is above about 40%. And that was our low renewable scenario. And so what you can see here is that this is the best case where we have 100% deployment of alternative energy vehicles powered with 90% non-fossil electricity. That leads to reduction in CO2 emissions, reduction in PM2.5 concentrations, and reductions in premature deaths. So it's really a win-win across all of these different areas. So what about hydrogen? In what I just described, I wasn't saying electric vehicles, I was saying alternative energy vehicles, because there's been discussion of using hydrogen potentially for heavy-duty transport, but also perhaps for even lighter-duty transport. And that's something that some work has shown is really not a good use of it. I just wanted to quickly show you different types of hydrogen production. I just picked this up off the web as a way to point out that hydrogen is touted as this clean fuel. Nothing comes out the tailpipe. It's really great, right? But then you always have to ask, where does that energy come from to make the hydrogen? You have to think about where does it come from. It can come from coal, different types of coal. It can come from fossil fuels with the carbon captured and sequestered underground, which I'm a bit skeptical will ever actually amount to very much. It can be made using natural gas with no emissions captured. It falls here. Almost all the hydrogen that's used in China right now is made from coal. Almost all the hydrogen that's used in the United States right now is made from gas. It can also be made from electricity and heat from nuclear reactors, and it can also be generated using renewable electricity. So these are electrolytic processes where the electricity zaps the water molecule and breaks off the hydrogen. What they don't even show here is the idea of electricity from a carbon-intense grid, from a coal-intense grid. So this is the best option, the green hydrogen, produced from electrolysis by renewable electricity. But in fact, no grid right now is renewable, right? And in China, there's subsidies right now that are going into hydrogen produced electrolytically. That means hydrogen can be produced from power that comes off the grid, the coal-intense grid. So that has the major downside that actually can increase CO2 emissions relative to making the hydrogen directly from coal. So not a good idea. So we looked at, on the supply side, at subsidizing grid-based electrolytic hydrogen and how much that will increase greenhouse gas emissions in coal-dominated power systems. And here you can see that the lowest electrolytic levelized cost of hydrogen by source and province in 2025. So in purple, grid-based hydrogen. This is the cheapest way to make electrolytic hydrogen in China in 2021. Solar in a couple of provinces and wind in the others in green. So the subsidy increases required to cost competitively produce renewable-based rather than grid-based hydrogen in 2025 in each of these provinces is shown here. And this is, again, Li Chunpeng, former PhD student. And then this is the corresponding decrease in CO2 equivalent emissions from producing renewable-based rather than grid-based hydrogen in 2025. And so this is a clear example of how important policy is. There can really be unintended consequences of policy to support electrolytic production of hydrogen. It can increase your emissions rather than decreasing them as are intended. And that in some cases, the costs, the subsidies that are needed to increase the renewable penetration are really not that large. Some of them are like 50 cents per kilogram of hydrogen, 50 cents in US dollars. And you can get large reductions in your CO2 emissions from that approach. So subsidies on grid-based hydrogen increase CO2 emissions, even compared with coal-based hydrogen, because grid electricity still relies heavily on coal. Economic support for non-fossil electrolytic hydrogen is critical to avoid an increase in CO2 equivalent emissions as hydrogen production rises. And large decreases in CO2 equivalents result from producing renewable rather than grid-based hydrogen in 2025. So there's possibilities you can couple your renewables directly with your hydrogen electrolyzers. And that direct coupling allows a guaranteed production of carbon, very, very low carbon hydrogen. This is on the demand side. This is work that's being led by Yuji Wu, a current PhD student in my group, based on the US. But here we're trying to rank the different end-use applications of where should hydrogen be used, because it's not just a supply side issue, it's also a demand side issue. And in some applications, there's a lower carbon intensity of using that hydrogen. In others, there's a higher carbon intensity. And in some cases, there's a lower levelized cost of carbon mitigation. In others, there's a higher cost. And so in some sectors, we found hydrogen really should be used. Green hydrogen should be produced, and it should be used in oil refining, ammonia production, and steel making. And in other sectors, it absolutely should not be used because better alternatives exist. And that includes personal light-duty vehicles, commercial light, medium, and heavy-duty trucks, and even in freight trains. Because electricity works really well there, and there's a loss of energy every time you make an energy conversion. From one form of energy, you go from coal to electricity to hydrogen, you're losing energy at each step of the way. And so these do-not-use sectors are really important to avoid. And yet, again, there's policies which can be have unintended consequences. In the US, we're subsidizing hydrogen as a commodity, bringing down the price of clean hydrogen, making it attractive to use in places where really better alternatives are available. So now we come to this idea of what do you do about these hard-to-abate sectors? These hard-to-abate sectors include things like oil refining, ammonia, and steel making. And that can be where green hydrogen is really valuable. It can also be where you can have synergies between industries. In the past, people have always thought about looking at single industries in isolation. And in fact, you can have integration of industries together, and they can facilitate reductions of emissions from both. So we've looked at synergies between hard-to-abate industries and how that can facilitate decarbonization. You can see here that industry is about 30% of emissions in China. And so there's opportunities in co-production of steel and chemicals, deploying on-site green hydrogen to decarbonize China's coal chemical sector, and benefits of infrastructure symbiosis between coal power and wastewater treatment. And I'll show you some examples of these. This work was led by Yang Guo, who's a postdoc in my group, who's now a professor, assistant professor at National University of Singapore, and Jiayi Liu, who's currently a PhD student here, with some collaborators from Tsinghua again. If you look over here, this schematic, I think, shows nicely what the idea is. So here you can think of this as independent production. Here you have steel plants, and here you have coal chemical plants, and there's no connection between them. The steel plants produce what's called off-gas, which is hydrogen plus CO. About half of that is used for electricity generation. It goes into gas turbines, and it goes back to the steel plants. The coal chemical plant side, there's coal, and it's then fed into the chemical plant and used both as feedstock for carbon and for heat. The co-production of steel and chemicals links them. So the steel plants, that excess off-gas, instead of all just being sent to the gas turbines, some of it gets sent to the coal chemical plants. So they use less coal, they emit less emissions, and they still make their chemicals. That means then that the steel plants need some additional power to operate the plants, and that additional power can come from renewable electricity or nuclear power. So you can reduce your emissions of carbon by switching away from these really independent processes. We found that co-production can reduce greenhouse gas emissions by about 7% and costs by about 1%, so it's about break even without policy support. But a high carbon price, which China is considering, increases the benefits to a 22% reduction in greenhouse gas emissions and about a 10% reduction in costs. And what's interesting, this is again this kind of analysis where we try and figure out how can you link these facilities. So we have very complex maps where we look at where the steel plants exist, where the coal plants exist, how can we pipe things between them. What happens if China is really developing more in the West? Can these things be built together to take advantage of these synergies? We find that 60% of the greenhouse gas mitigation and cost reductions can be achieved by around a quarter of all the potential connections. So there's potential here for big reductions if thought is taken now into thinking about how can you use these hard-to-abate industries to help reduce emissions from them separately. Another thought is how about deploying on-site green hydrogen to help decarbonize China's coal chemical sector? So here you have a coal chemical plant and green hydrogen production. And these chemical facilities have land around them which could be used for producing solar energy. And that solar energy could be used locally to produce green hydrogen. The coal chemical plants, as you saw, are potential large consumers of hydrogen, and this is really a potential opportunity for decarbonization. This again was Yang Guo's first lead on this. And then finally, his third paper while he was here was to look at benefits of infrastructure symbiosis between coal power and wastewater treatment. This is again a similar idea where you can think about these wastewater treatment plants. They produce sludge. That sludge can go to the coal-fired power plants to be burned. They produce water. That reclaimed water can go to those coal-fired power plants for cooling. So the wastewater treatment plants have large volumes of water, and sludge generation and land scarcity pressures are both increasing. So figuring out what to do with this sludge is important to them. And incineration is an attractive option to get rid of it, though I keep feeling concerned about if you incinerate this sludge, what happens. You need to have very good pollution controls on those stacks to make sure you don't end up transporting all of the volatilized plastics around the world in the air. But coal-fired power plants are the largest emitter of CO2 and second largest consumer of water, ranked after agriculture in China. And so they also face decarbonization pressure from market competitiveness due to decreasing renewable energy costs and policy due to the carbon neutrality targets. So linking them is helpful. So here we looked at coupling municipal wastewater treatment plants with coal-fired power plants. And what are the cost-effective linkages between these power plants and what wastewater treatment plants that exist? And then we found that this carbon reduction can be about 30% of what the wastewater treatment sector emits, and about 60% of the water consumed by the coal power sector. And it's a net cost savings. And again, attention needs to be put on stack controls if this is implemented. Again, a few linkages achieve the majority of reductions. 30% of the sludge, 40% of the water leads to about 80% of the carbon, water, and economic benefits. So these infrastructure synergies are really cost-effective opportunities to help reach China's climate and water conservation targets. So I'm just showing this slide to come full circle to say that we've looked at demand-side approaches, supply-side approaches, what to do about these hard-to-abate sectors. There's opportunities in all of these areas. China is very seriously working to address this. I just gave a talk by Zoom at Tsinghua last week and asked, like, how many programs are going on at Tsinghua right now on carbon neutrality? They have at least half a dozen. There's people in the government who are engineers who are technically trained. This is a high priority of the Chinese government. So in that sense, it's very exciting to work on China because you feel like what you do actually makes a difference there. They really listen. And they are making progress. Though, as you saw, their emissions are continuing to increase. Their economy, as it grows, needs more power. As they electrify more and more of the economy, the power demands grow. And so how they actually provide that power will be extremely important for the future of the planet. So with that, I'd like to thank my group. The key people here were Mi Zhou, Jia Yi, Yuji, Yang, and Sheng Wei. And I welcome questions. Thanks for your attention.
Questions for our speaker? Do you want to take them?
Sure.
Thank you for a crystal clear, excellent talk. It was utterly fascinating. My question is, how many times have you been to China, and to what extent has your research been a help to the Chinese going forward?
So I've been to China until COVID probably every year for 20 years. And I was just back there for the first time this past May. And one of the things that totally struck me was that I was there in 2013 during the airpocalypse when you couldn't see the building like across the courtyard there because the smog was so profound. And I used to show a picture in my talks showing me and 3 Tsinghua professors with masks on. They said, you have to put the mask on. We can't go to dinner without the mask. And when I was there in May, I realized Beijing is surrounded by these beautiful mountains. You could actually see the mountains even from the airport. It was stunning improvement. So I'm super impressed with how much China is committed to doing. And many of my group members are Chinese because I wanted to work on China, and the Chinese are really serious about training people up. And many of them have gone back. I have students who are professors at Peking University now and other parts of China. So I think that they invite me to give big talks for nature conferences and stuff. So I think that they do listen. They're like a sponge. They want information wherever they can find it. And I see great promise. Yes, Ken.
Thanks so much. That was really wonderful. So just building on that, I'm looking for a plus and a minus. So when you're thinking about Chinese ambition going forward, what do you think is either at the policy level or in terms of engineering or pilot plans, what do you think is the thing that gives you the most optimism? And I talked to a lot of Americans who are really skeptical that China is really ambitious. And then on the flip side, what do you see as the major challenge or thing that makes you skeptical of success in Chinese decarbonization efforts?
So that's a good question. I fully recognize that right now there's huge tensions between the US and China. And politically in Washington, there's grave concerns about China for a whole bunch of security issues that are front and center in the minds of people in DC. In terms of the work that I do, I've not seen any obstacles to continuing to collaborate at a personal level. People are super interested in coming. They're super welcoming to have us go. They're very eager for thoughts and input. I guess what makes me optimistic is this what I think is very serious intention and efforts. What makes me really concerned is that their emissions are enormous, right? If we go back to that slide, their emissions are absolutely enormous. Their economy is continuing to grow. They're electrifying. They electrify with coal power. It does not help with CO2 emissions. They've got to get away from coal. The workshop I was involved in last week by Zoom there was a person there talking about small-scale nuclear reactors. They're really looking across at everything. And you can see that they're the biggest renewable producer in the world, and they are producing cheaper, and they're going to be influential and important in decarbonizing the world, for better and for worse, right? Because we probably would like to have more competition. So it's just the scale of the problem that's, I guess, concerning. The commitment, I think, is real. Yeah.
Thank you very much. Very interesting. I was interested in the acceptance of heat pump technology in China. So I followed 2 years ago the discussion in Germany closely, where the government wanted to bring in a new law with much stricter rules, which are very much in favor of heat pumps. And then there was a huge campaign from media and opposition parties and even the Liberal Party within the government against this heat pump expansion kind of.
Why?
That the minister himself would come out and go in the cellar of an old lady's house and crack the old heating out of these unbuilt spheres. And so
What's the concern with heat pumps in Germany? Didn't follow
it
that.
was not really rational. It just was irrational by changing technology. And it even led to a spike in gas, and so people then bought in gas heating sales because people were afraid that in 2 years from now, so they could not install new gas and stuff.
You mean gas furnaces?
Gas furnaces, yeah. Gas furnace, yeah. So completely irrational behavior. I was wondering in China, is the government very much pro-decarbonization? Is there some skepticism against heat pumps, or is it just accepted as a modern technology?
So that's a good question. I actually don't know broadly the answer to your question, but Beijing is subsidizing the installation of heat pumps, and they have adopted air source heat pumps in buildings there. Our work was recommending heat pumps. We didn't analyze the sort of social acceptance of them at this point.
A curious question: when you are maybe some farming village far away from Beijing, how would you react when you present technology?
I mean, the challenge far away from Beijing is those provinces are poorer, and in the north they're cold. And there's a challenge because to get a big heat pump, it's expensive. That's where the energy efficiency of the building, the improvement in energy efficiency of the building first is really helpful to bring down the size of the heat pump you need, to bring down the cost of the heat pump. So that's a good question. I don't know if anyone here knows anything, knows any answers about that. So yeah, I mean, in the US we have big subsidies on heat pumps, and we actually installed our heat pump, which works beautifully, we have no problems, before the subsidies came in. But the challenge here is that the contractors are oblivious. For the most part, the standard contractors don't know what they're doing, and so you talk to them, they're like, oh, why would you want to do this? It's really expensive, it's really complicated, nobody else is doing it, the sort of standard social norm argument against doing it. And then you talk to people who've done it, and you find the 1 or 2 contractors who know what they're doing, and they come in and they installed it for us at basically exactly the cost of a conventional system. And
That's similar in Europe. Many contractors that have been building gas and oil furnaces for decades are skeptical, and then would maybe more favor against it if somebody's interested because they have technology.
yeah, right. Mm-hmm. Yes.
Yeah, excellent research. My question is, so if you track the growth of the Chinese economy with the consumption, it's almost like a parallel line. So now we're all reading about the Chinese economy kind of slowing down. Do you see a sense that there may be a tension, struggle between those who want to do the green transition versus those who are really nervous and really want to do the green transition?
So that's a good question. I asked a very similar question when I was there in May of everybody, which was, do you think that curve is going to look, 2030 to 2060, a straight line like I drew, or stay high and come down late, or drop quickly and have a long tail? I would say actually everybody I asked that question to said it's going to stay high and come down later. And so that would argue that, they really are concerned about their economic growth, and so they will focus on that as the primary thing. But I think they will peak at, maybe a little bit before 2030, but around 2030.
Let's take one more question.
Mm-hmm.
Yeah, thank you for the talk. Very fascinating. But the impression that I got is that it's a very top-down, very stakes-driven approach to bringing down CO2 emissions. And I was wondering if there is a change, if you sense a change in the Chinese approach in that way, whether the state is trying to bring in civil society initiatives, how could a more bottom-up or an inclusion of bottom-up approaches improve CO2 abatement in China?
I don't know how the improvement of bottom-up would, I don't know the answer, but I guess the top-down has had huge advantages in moving really fast. Certainly there's been, human dimensions that have not always gone as everyone would like, but the top-down approach has been extraordinary in like building transmission lines, high voltage transmission lines from west to east. They have dozens of high voltage transmission lines. We're struggling here. How are we going to ever build enough transmission to move our renewables to the center? So this top-down, it's not a perfectly top-down system, of course. The provinces have some level of autonomy and they have certain interests of their own, but that has been their mode of operation and it has been effective. If there was bottom-up efforts and concerns, I think that would be helpful, of course. But my research hasn't looked at that, unfortunately, so I can't really address that question.
Well, Professor Mauzerall, thank you so much. I want to thank you for an interesting and engaging talk on what is clearly really important research. Thank you so much.